Hello and welcome to what might well be the first spatial awareness hangout, where myself and my esteemed colleague Chris North, who is visible and in Cardiff, will talk about some of the exciting things that are happening in probably astrophysics, maybe planetary science, and perhaps even space travel. Depending on our future budget. We're joined for this Rosetta special by an old friend of ours, or at least a drinking companion, Professor Alan Fitzsimmons from Queen's University Belfast. Those of you who watch Sky at Night will have seen Alan as our companion and guide to comets back in November when we were chasing Comet Ison down. But Comet Ison is old news. This year's comet of choice is Comet Churyumov-Gerasimenko, is something close to that, which the ESA Rosetta probe drew alongside yesterday morning in a very small but exciting maneuver to become the first probe to travel alongside a comet. And Rosetta is going to be a spectacular mission with a whole string of firsts, Chris.
Yeah, it's a great chance to actually go and study a comet really close up for an extended period. The only thing we've had before is comets flying past, spacecraft flying past comets.
So both, in fact.
Yeah. So we had a few years ago. We had Hartley 2 was flown past by was that Epoxy? I forget now which mission it was. And we had Giotto going past Halley in the 1980s, and there's been a string of others, Vil 2 by Stardust and so on. But these have all been fleeting glimpses of what's going on these comets. And to be able to study a comet really close up, it means we get a way to study material that's essentially been there since the start of the solar system. Although it has changed slightly, it's had far less change happen to it than things like the planet Earth has, and even the Moon.
Good. So comets are exciting. And Alan, what do we need to know about comets from the very beginning, just to understand why Rosetta's exciting? They're usually described as dirty snowballs.
That's right, and we already know a lot about comets. We know that they come from two source regions out there, the Kuiper Belt beyond Neptune and even further out the Oort cloud. We know, as you say, they're quite often called dirty snowballs. They're about at least 50% water ice, and there's kind of bits of rock and dirt and primordial stuff mixed in there. And effectively, we believe that all these comets formed at the start of the solar system, but they've been kept in deep freeze since then. And so when we get a comet, what we're doing is we're looking at the stuff that was around 4.5 billion years ago when our solar system was being put together. And so first of all, it tells us something, we hope it tells us something about what conditions were like back then and what was around. Since then, of course, when we see a comet, it's in the inner solar system and it evolves. And we also want to understand that evolution process. We want to understand whether or not it affects what we measure with telescopes and, of course, with spacecraft. And we also want to understand overall what happens to a comet during its relatively brief life in the inner solar system.
Yeah, this one, Churyumov-Gerasimenko, that's 2-0 to me, by the way, people, has moved into the inner solar system, right? That's happily, it's what's called a Jupiter family comet. So that means it splits its time between roughly Jupiter-like orbits and somewhere inside Mars's orbit but outside Earth's.
That's right, and in fact, right now, the orbit of 67P, I'm going to stick with that one, is basically changing every time it goes around the Sun, and occasionally it will suffer quite a large gravitational kick by Jupiter because its most distant point from the Sun is pretty much at Jupiter's orbit. And that can change its path around the Sun, its orbit, quite dramatically. Now, we don't know that means what the exact history of this comet is. We believe it evolved from the Kuiper Belt sometime over the past few million years, and it's probably only been in the inner solar system for about a few tens of thousands of years, because it won't last that long.
When we take observations of comets from the Earth, they have these spectacular tails showing the stuff that's come off the comet and been sent outwards by the pressure from the Sun. But it's really that material on the comet, as you've said, Alan, that really helps us understand what's taking place. So how much does looking at the surface tell us that just looking at the material in the tail doesn't?
Well, what it's telling us, first of all, is, as I said, how these comets evolve. Because when we see the material from Earth, we never really see the nucleus and when it's active, because it's hidden from us by the surrounding dust particles and gas molecules and ions that have been released from the surface. So we can't actually see that process happening in real time. And although, as you mentioned at the start, we've had these fleeting glimpses by spacecraft flybys of other comets, Rosetta is going to be the first mission to actually provide us with a ringside seat of what happens as a comet moves in towards the sun. And when it does so, what it'll be telling us, first of all, is where does this material come from? Does it come from some of these flow-like structures that we've seen on the surfaces of comets? Does it come from one of the old pictures we had? There'd be cracks in the surface, and this material will come out in jets from these fissures in the surface. Perhaps that's happening. We don't understand it. One possibility that came from the Deep Impact mission to Comet Tempel 1 almost 10 years ago now, back in 2005, was that we do see these scarps, and maybe the material is coming off the faces of these scarps as they're heated by sunlight. We simply don't know where that material comes from, and that could be important for understanding what the makeup of a comet really is, because that material is undergoing different reactions as it's baked in sunlight, and also different chemical reactions. So we really do need to know what's going on at the surface.
So that means we need high-resolution images, and we need to watch the story unfold, both of which we'll do. But even the first images that came out as Rosetta approached comet Churyumov-Gerasimenko 3, they're even consistent. As Rosetta approached, there were some surprises. Frankly, I'm not sure that anyone would have drawn what are we calling it these days? A rubber duck, and called that the typical shape of a comet nucleus? I mean, were you surprised, Alan, by the shape? Chris, have we got some of the? We've got a rotating image, I think, of the early.
Yeah, let me just try and find it in my my folder and bring it up.
But while Chris does that, Alan, were you surprised? I don't know why I expected it to be spherical, but I did.
Well, we did expect it to be spherical. In fact, there were already two models of the potential shape of the comet generated.
Based on data from Earth.
One by Philip Lamy using Hubble Space Telescope observations, a limited amount of those, and one by Stephen Lowry, who'd used a lot of observations from the ESO telescopes down in Chile. Now, neither of those shapes predicted exactly what it looked like, but we know that there are limitations in trying to decipher what a comet nucleus looks like when you only see it as a point source. And so right now they're comparing what we actually know of the shape with the models and with the ground-based observations to see how close they were. But neither of the models really predicted this bilobe, this double-lobed shape of the nucleus. So as you say, it was a surprise. We have a number of comets that we've seen resolved, so we can make out at least the rough shape of them in the past. And only one of those has had this double structure, this binary structure that you might call, and that was Comet 8P Tuttle, which was imaged by radar when it flew past the Earth a few years ago. But that was just one. And so, to be honest, most of us thought it would be irregular. Small bodies are irregular because there's not enough gravity to mold them into a ball like the Earth. But we did expect it to be. We didn't know that we really expected that shape, and it was a big surprise for everyone, I think. But a wonderful surprise. There's history and there's science there that we need to unravel.
I think I can share the. I showed it a couple of seconds ago, but there's the image of the comet there rotating as Rosetta approached, this rubber duck type shape. And as you said, we can compare that with another image. So you mentioned Comet Tempel, which was flown past, I guess, a good few years ago now, and that's the kind of thing we saw before. So a largely roundish object.
That's right, but and most of them have been vaguely round, as I said. But if I can do this trick, And if I can show you radar images,
we could send a probe to Rosetta. Can we share an image from Belfast?
Yes. Okay.
Yes.
So can you see? Yes, excellent. So if you can see that, now these aren't clear by any means. You have to look at them. And Chris, I think you said it looks a little bit like a seagull flying towards you at one images. But one can see that these are radar images from Earth of this nucleus when it flew past a few years ago. And you can see very clearly that there are two objects there in mutual orbit. So this was our first example of what we would call a binary nucleus. But it's only one, as I said. So we weren't expecting anything quite like what we saw when we got to 67P, Churyumov-Gerasimenko, 3-1, Chris.
Yeah, yep, very good.
But what we still don't know is whether or not this is truly a binary object, because that's certainly one possibility, that this is a binary that formed out there in the Kuiper belt before it was brought into the inner solar system by perturbations. And so it could be a primordial binary object, which is incredibly exciting.
There's an image up now showing the objects in closer detail. So while it looked like a rubber duck before, and I think everyone when they first saw it said that looks like a binary object, but the case is very much less clear cut in many respects, right? Because there's no obvious neck region between two objects that looks.
Yeah, but if there was a neck, don't you expect material to end up settling there just from gravity? So if stuff is moving about near the surface, you'd end up filling in the neck, wouldn't you?
That's right, and that's what's suspected happened in another comet that's been flown past by a spacecraft, Comet Hartley 2, which was flown past by the Epoxy mission.
Which was Deep Impact, right? And then got renamed for reasons I do not understand. But yes, yeah. But Hartley 2. So yeah, that looked like a battery with material around a pinched waist, right?
That's right, and that pinched waist, that material pretty much follows what we would call the gravitational potential between those two objects. If you assume it's just two objects with stuff settled in between, while just following local gravity, that's where you'd expect it. And Chris has got another lovely image up there showing it. That's fantastic.
Yeah, so, it does look like a spacecraft, that one.
That does look a little bit like a spacecraft as well, or actually like a drumstick to me, but there you go. I only had a light lunch. So the question is, is this really a binary object or not? And one thing we hope to get out of Rosetta is a definitive answer, because once it gets into a close orbit towards the end of September and into October about the nucleus, then it should be able to sense the local gravity field, and it will be able to see whether or not that material in the neck is roughly the same density as the two ends,
right? Or
whether or not it's very low density. If it's very low density, that would imply it's loose material that's accumulated there, so it is a binary. If it's the same density all the way through, then there's another reason for that shape of that nucleus.
Yeah, and which could presumably be something like this is an active object. It's swung around the inner solar system. I mean, this is its first time round, right? We know it's been going around since the 60s, presumably a lot longer than that. So it could have just been processing. Maybe that's where previous eruptions have hollowed stuff out.
That's right, and one of the other images that was released by ESA yesterday showed these lovely jets coming out of the nucleus, these jets of material caused by the ices on the surface sublimating and streaming out into space, carrying with them the small ingrained dust particles.
Yeah, we'd seen activity from the comet all the way back in April, if I remember correctly, and there was a couple of weeks of activity, and then it quieted down again. So these jets were, as far as I know, the first sign that the comet is waking up and is active, which is exciting. But Alan, I know you're involved in the ground campaign, so it seems ridiculous that we've spent the space probe there, we've spent €1 billion, which is money well spent, and we've spent 10 years to get there, and you're still trying to look at Churyumov-Gerasimenko from the ground. I mean, A, what does it look like? What do you see from the ground? And B, why are you bothering?
Okay, well, I can answer those questions of 67P Churyumov-Gerasimenko, 2.5 to 4, I think, if I included the number. I'll bring up an image we obtained this morning with the Very Large Telescope down in Chile. And here we go.
This is live publication of data, ESA, take note.
That's right. And if you can see that, can you see that okay?
Yeah, there's a smudge.
There's a smudge. Well, let me just change the colour scope.
So this is with what? One of the UTs? Oh, cool.
One of the 8-metre telescopes, one of the 8-metre units of the Very Large Telescope down there. Actually, let me change it slightly differently there. If I change the colours now, one can see very clearly.
Oh, yeah.
Yeah, you can see the central coma. That's about, we measured at about 1,000 kilometres across, and then stretching out now. If I zoom up, stretching up to the top left, one can see the dust tail streaming behind the comet. Now, why do we want to do this when we've got a spacecraft there? There's one very good reason. That spacecraft on this image is in the central pixel.
Ah, okay.
So Rosetta has a ringside seat of what's happening at the nucleus for the next year and a half. But once it goes beyond the nucleus, it's very hard to tell what's happening to it with Rosetta. So it's ground-based data like this that lets us follow that dust when it's released from the nucleus and follow it as it streams back and forms this beginnings of this dust tail.
Presumably, you want to see how those two things connect together, because then when you look at a different comet other than Churyumov-Gerasimenko, if you look at a different comet, you want to understand what might be going on at the nucleus using these Rosetta results. So you have to sort of be fluent in switching between the two.
Absolutely, that's right as well. And that brings up another important thing. We've studied literally hundreds of comets using telescopes just in the last few decades, let alone centuries. And so we have the huge body of data. And what we want to do is relate that body of data to what Rosetta finds. And the only way to do that is to make sure we've got the link between what Rosetta sees via what we see with the telescopes over the next couple of years to what we've got in our science archives.
One of the big things that Rosetta's seen that we've really never seen before is it's got the highest resolution images of the surface that we've ever had of a comet. And some of the structures on there are simply amazing. I mean, it looks like there's layers of material, and there's what they call a village of houses, a village of boulders, because they're house-sized boulders and so on. The structure we've just never seen in that detail, and hopefully we're going to see a lot more of that over the next year. So is that kind of layered material that we've seen, is that what we expect to see on a comet like this, Alan?
Well, absolutely. I mean, this is really exciting. I don't know if you, Chris, have you got one of those images you could bring up, perhaps of the middle region of the nucleus?
These were just out yesterday, weren't they?
That's right, that's right. Now, we've got to remember that we've still only got a resolution here of 2 meters per pixel.
Yeah, because the spacecraft is, what, 100 kilometers away, something like that, from the comet, but it will work its way in. We'll say a bit more about that in a second.
Absolutely, but even still, yes, we are seeing signs of layering in some of those eroded scarps and surfaces. Now, this is really exciting because it's given us clues as to how comets form. Because if you find layering on Earth, that tells you that material is deposited a bit at a time in different layers. And we see this in sedimentary rock, when we see material deposited that was at the bottoms of lakes and seas. And we see it in volcanic rock when you have individual lava flows. Now, neither of these can explain layering on a comet nucleus. So if that layering really does exist, and as you said, we'll know it over the next couple of months as Rosetta closes into the nucleus, then what that's telling us is that that material was deposited subsurface because it's subsequently been eroded by the comet being in the inner solar system. And so those layers must have formed during the time of formation of the comet. So what we would be seeing there is possibly some signs of the accretion process of comets 4.5 billion years ago, with individual small impacts depositing layers of ejecta around the growing nucleus. And if this is true, if this works out, this is incredibly exciting because we don't see that on any other body in our solar system. We are seeing physical processes that happened in real time using images that you can point at on a macroscopic scale, on a kind of human type scale, on a comet, and we don't see that on any other body. absolutely incredible.
And yet, when you look at particularly the image Chris has up now, I mean, if you'd shown me that before yesterday, I would have told you that was an image of the moon. You know, there are things here that look cratered. That looks like a rill at the basement of a lunar sea, and a long winding channel.
Yeah, very careful about that, because look at that image really closely. At first glance, it looks like a rill, but look at the shadowing and look at the layer outside. I don't think that's a rill. I think that's
these regions, Alan.
Flow. That's one flow of material on another flow, overlying another flow of material.
Right, so it's a jagged edge between the two. But the broader point, though, this looks like a crater. And in fact, I saw lots of people, if you look at the images yesterday, were talking about the craters on the comet.
Yeah.
We need to be slightly careful. In astronomy, when we say crater these days, we tend to mean impact crater, something that's slammed into a surface.
Yeah.
And craters means old surface. So you could jump to the conclusion that this is a relatively old cometary surface, but that would be nonsense, right? This is something else is going on here.
It could be, yeah. It could be. It might not be. It's again. This is the first time we've got these images, and it's going to take a long time to understand them. So there's two possibilities here at least. One of which is that what you're seeing are sublimation pits. This is material. This is where material has left the comet nucleus in the past, and that's produced the coma and the tails that we see. But over time, that material has either been filled in with material from other parts of the comet through near-surface flows, which we know can happen, or it's been covered by its own dust. That's one possibility. Another possibility is that you're absolutely right, and people are right. These are old craters, but these aren't craters that formed over the past few million years. These are craters again that formed 4.5 billion years ago, during the formation of the comet, were covered up by all the other impacts, and now are gradually being revealed by the erosion of the nucleus. There's just two possibilities. There may be other possibilities for these landforms. This is a very peculiar place. It's not like any place we're familiar with naively, because the gravity is really low. It's continuously eroding every 6.5 years when it goes around the sun, and so there's a whole rake of different geological processes and physical processes happening at the surface of a comet, and this is exactly what we need Rosetta to understand.
I think one thing that's going to happen with the mission in the next few months is that they have to pick one particular location on the comet to go and check out with the lander, with Philae.
Yeah.
The lander. So Alan, given your knowledge of comets and what we've seen so far, I guess the €1 billion question maybe is where would you pick to go and land on this comet, given the knowledge so far? Could you narrow it down, do you think?
And let's ignore activity, right? Because obviously you're not going to land on the source of one of those nice jets. So let's ignore that. But
although, funny enough, you might want to land relatively close to one. So
hey, it's not your spacecraft. Don't take risks.
Serial. Sorry, yes. Okay.
I think they also said their landing ellipse, the area that they might land within, is about a square kilometre in size. So I'm not sure how accurately, when they pick where they're going to go, they can pinpoint where they're going to land.
Well, they're doing best they can, and hey, they're pretty good at what they can do. They've got to the comet in the first place, which isn't easy. It's taken 10 years, yeah. Where they land, I mean, you've really got to worry about the land. The land is pretty robust. It's designed to land on slopes of up to 30 degrees and so on, and it's got this three-legged construction where each of the legs moves individually. So it's pretty good, but clearly, what's going to happen is that over the next couple of months, they're going to pick potential landing sites, and when Rosetta moves in closer to the nucleus, that's when they look very carefully with the OSIRIS camera, the narrow-angle camera on OSIRIS, I should say, very high detail to look at those different terrains to see where it might be safest. Wonderful thing was that about 2 months ago I was in Germany, where the members of the camera team are, including Holger Sirks, who hopefully a lot of people saw yesterday.
Yeah, he's also on Sky at Night this Sunday, 11 p.m. BBC4, amongst many other good things. But have to mention these things.
Well, quite right, and Holger's the person to talk to because I asked Holger a couple of months ago, how are you going to pick where to land the lander, where to put the lander, Philae? And he said, well, Alan, we're going to try and pick the most boring place on the comet because we just want it to get down safely. And right now, the problem is that there isn't a single boring place on the nucleus. It all looks incredibly interesting.
Well, the closest you've got to boring, which if you think about the rubber duck, is the bottom of the duck, will be in shadow when they're trying to do the landing. So you can't land on the most boring place.
Well, it's some of it's in shadow. They've got to be careful. That's right. Remember that the comet's rotating just over once per 12 hours. Okay? And the bottom of the duck, if you like, so we're going to have to come up with better terms.
No, I think everyone knows exactly what you mean if you say the bottom of the duck.
Fair enough.
The head and the body certainly make sense, right? When talking about the two lobes.
Yeah, exactly.
Yeah, well, that's fair enough. Okay, so the bottom of the duck or the body of the duck.
If it makes you feel better, bottom of the duck is now the BD.
The BD, thank you. Right. The bottom of the anyway. That region is in sunlight once per orbit. Once per spin of the nucleus, because we can see it. We've got images of it. Yeah. But the problem is that it's not in continuous sunlight. And the lander has the batteries on board, and those batteries should last for about a week.
Yeah, I mean, most of the mission, Tina Cowan, by the way, I want to know how long will the lander be able to communicate. The main mission is about 60 hours, right? That's the conservative. So you go to all this effort, you get there, you land, and you only have 2 and a bit days.
Yeah, but the important thing is that, well, okay, the batteries can last up to a week, but 2.5 days is the nominal mission, that's right. But there are solar panels on the lander, so that if they continue recharging the rechargeable batteries on board, then in theory, Philae could last a lot longer.
But I mean, it's going to be a pretty dusty, scary place by then. Actually, I mean, how nasty an environment is this going to be? We've got the lander to survive, but Rosetta's also flying around because it's a European mission. It has to use solar power. Yeah. We don't like launching the nice little nuclear reactors that the Americans use, so solar power in the relatively outer solar system. But that means it's got these 32-meter long sails. How dangerous an environment is this?
Well, it depends exactly where the jetting material is coming from on the nucleus, okay? Because when we see it from Earth, when we see the coma, even then we can see that there are regions of the atmosphere where there's many more dust particles than others. So if, for example, they can get an orbit, or they can at least get a trajectory where they avoid most of the large dust jets, it's not too bad. But near the nucleus, that dust may be coming off at several tens of meters per second, or hundreds of meters per second when it's close to the sun. And so to minimize basically the scouring of the spacecraft, they may have to move it out from the nucleus when it's coming in even closer to the sun, just to get it into a lower dust density environment. But remember that. Sorry.
Well, I was going to say, I know they've also said that in these initial phases, they're keeping the solar panels rotated so they're facing the sun, but a perpendicular, the direction of the comet is in line with the solar panels, so they present as little area as possible. And that's not just to minimize impact from dust, but also to minimize the drag on the spacecraft by the dust coming off the comet, which means, of course, its orbit will change and causes headaches for the flight dynamics teams.
That's right. Again, going back to it, this is such a small nucleus, or actually, it's not a bad-sized nucleus for a comet nuclei. It's we've
about 5 kilometers across, right?
That's right. That's right.
That's from beak to tail, of course.
That's from beak to tail, exactly. Not including the webbed feet.
Hey, if it grows webbed feet, I think we have a different story to tell.
Yeah, that goes back to the whole origin of life thing, doesn't it? But anyway, that's right. But you've got to remember also that the spin axis is fixed in space. We think this comet, all indications that this comet is in what we call simple rotation, so that the spin axis is staying fixed in space. And as the comet goes around the sun, the orientation of that spin axis to the sun will change. And so that's good for one thing, because if there are any regions not being illuminated at the moment, by the sun. They will be eventually, or they should be eventually, as Rosetta follows the comet in and around the sun. But at the same time, you've got to worry, as I said, about where you've got the solar panels pointing as well, and how that interacts with the orbit dynamics. This is probably the most complex small body mission ever flown. Let's put it that way.
Yeah. And look, I've got one thought I want to ask both of you at the end, and I need to put this without insulting Herschel and Planck, which are two missions that Chris works on. But this is... Actually, I could quote Matt Taylor, who's the project scientist, a fabulous guy who was having a beautiful and wonderful meltdown on Twitter yesterday, singing song lyrics and so on. But he said to the BBC, to me as well, that he thought this was the sexiest mission ever, and it really is. It's not astrophysical, it's planetary science, so Chris, you get a pass. But this is a really sexy mission, and the sexy missions we've got used to NASA doing. Landing on Mars, the big Cassini outer sources, which had ESA involvement. But it's really nice, I think, from a European perspective, to have one of these missions be ours. I don't know if you both agree with that, but I think Rosetta's going to be a fabulous ride.
I think I agree that it's great to see an ESA mission having sort of the publicity and the excitement behind what is an exciting mission, because that's sometimes something that's missed, and hopefully it will mean that it might help mean that people don't get ESA and NASA confused quite as much, which is a common thing. People assume a lot of missions are through NASA, and of course they're not. And I mean, one has to hope that this will really kind of inspire people into thinking that it's not just America that does this, even though most NASA missions are international to some degree. That those are done over here as well, and the ESA is a big player in this kind of game.
I completely agree as well. In fact, it's always disheartening when you find yourself talking to a group of people, even school children. They've all heard of NASA, but none of them have heard of ESA, even though we've now we've rendezvoused with a comet. ESA has landed a probe on Titan. ESA currently has missions orbiting Mars and Venus. People don't seem to know this, and hopefully this will allow people to take some pride in the fact that as part of the European Space Agency, the UK plays an awfully big part in the exploration of our solar system and beyond.
Yeah, we'll talk more about that, I'm sure, as we head towards the landing and indeed all the science as Rosetta creeps towards the comet. So, Alan, thank you very much for joining us. Chris and I will be back. I'm sure we'll grab you again, Alan, maybe as Philae descends towards the surface, which comes up on November the 11th. Thank you all out there on the internet for listening and watching, if indeed you have been. We'll talk to you all soon.
Okay, bye.
Bye.